Is this too loud, too quiet? I'm not, it's just okay. You'll find out if it's too loud when you find out if you like the talk. Okay, so I've been a great admirer of this conference for quite some time as a consumer or user of computational ideas, if not actually a generator of said, and it's all the more an honor to be a part of it now, at least in some small way. So I'd like to thank the organizers for bringing us all together and for the small lapse of judgment which invited me too. So I'd like to tell you today about some ongoing work with Julia Gordon at UBC and Ali Altug, who I think is still at MIT for another couple of weeks. And the motivating question, such as it is just this. How big is an isogeny class of elliptic curves over a finite field? And it's a little silly giving a talk like this here because most of you already have great ways of thinking about the size of an isogeny class of elliptic curves over finite fields. And even if you didn't, after Stefano's talk yesterday, you'd have absolute confidence that somewhere there's a button you can push which will answer this question. Which means that the whole talk has a bit of a feel of an old episode of Columbo, where you, the reader, like at the beginning, you see the crime happen. And then the pleasure, such as it is to watch the investigator bumble around without the knowledge that you have, trying to put together the answer in some other way. And so with this context, we begin. All right, I'm going to remind you of something which is in your blood probably at this point, which is that if you're fortunate enough to have not just one but two elliptic curves over a finite field, you can, isogeny is a geometric relation. There's a non-trivial map from one to the other, but you can measure this with just a simple point count question. So it turns out that two elliptic curves over a finite field are isogynous exactly if they have the same number of points over that finite field. And we can use this as our working definition now of what it means to be isogynous. Equivalently, these numbers A, these traces of Frobenius, and these are the same traces of Frobenius which showed up in Alina's talk, determine the characteristic polynomial of Frobenius. So Frobenius here, I'm thinking of it as acting on, say, one of the Tate modules. So and those have rank 2 over ZL. So I have an operator. So I get a quadratic polynomial, so it's monic, so there's that term. I know it has determinant Q, so there's that term. So the only ambiguity is in what's that middle term, what's the trace? And so that's why the trace of Frobenius, for small values of y, determines the isogeny class of the elliptic curve. And so let's let I of AQ or I of AFQ just be the isogeny class of this set. Sorry, the set of all elliptic curves with this trace of Frobenius as opposed to some other trace of Frobenius. And so I'm trying to say, what's the size of this set? Or maybe I will count a little more intelligently using a mass formula type approach as in Shafu's talk, and then I'll weight everything with 1 over the size of the automorphism group. And that's probably the right way to count. Most of the time, they'll all be so vague you can't tell the difference between which way I'm counting. If there are questions that arise, by the way, I'd be happy to entertain them. So just to remind you, none of you is naive enough to do this, but but I am. And so the first time I thought about a question like this, here's what I did. I thought, all right, well, you always have to say, well, when you're making a sort of half-assed heuristic, which probably won't work. So I know that this trace of Frobenius, this number lies between minus 2 root q and 2 root q, because it's the sum of two Weil numbers, and they each have size root q. And I also know that there are about q elliptic curves over fq. Whether or not this is exactly right depends on how I choose to count. And so for one, as a null hypothesis, you might guess, all right, I've got q elliptic curves. I've got on the order of root q bins. I could put them in really for root q, but since this heuristic is wrong, I might as well pretend it's root q. And so I wind up guessing, all right, I bet an isogeny class has about the square root of q elements in it. And of course, at this point in the conference, even if you didn't know this is wrong, you know it's wrong, right? So there are all these wonderfully interesting distributions that happen. It's not flat. It wasn't wrong to try it, but this isn't what actually happens. So the second guess might be, well, I remember there's a Sadotape either conjecture or theorem, depending on exactly how you choose to formulate it. But roughly, so the way it's most commonly stated, I think, is you measure an isogeny class not exactly by the trace of Frobenius, but by the Frobenius angles. And so if we were to factor the characteristic polynomial of Frobenius over the complex numbers, these numbers have size root q. And so the only ambiguity is in what are these angles, these thetas. And so the Sadotape distribution is the distribution which says the odds of getting an angle between this and that are like is basically the integral of sine squared theta from this to that. You have to normalize it so that if you go over all possible angles, you'll get one. But if you do so, you get this measure. And this measure has shown up in a couple of different contexts already in this conference. I want to remind you, in anticipation of what's happening a little bit later, that this doesn't come, it's not as arbitrary as perhaps it looked the first time that you saw it. So one way of getting the Sadotape distribution is you have the space of unitary matrices, and that has a Haar measure. I mean, it has lots of Haar measures. It has a Haar measure which gives mass 1 to the whole thing. And then if you push that forward to the space of characteristic polynomials or Frobenius angles or any other measure of conjugacy classes, if you do the calculus, then this is the measure that you will get. And so that's where this measure comes from, is it's saying, we believe that Frobenius elements are really evenly distributed in SU2, and then one kind of shadow of this sort of geometric or group theoretic equidistribution is a sine squared theta type distribution on angles. And so armed with this, you could say, all right, I'm going to pretend that the Sadotape distribution actually exactly gives me exact answers for sizes of isogeny classes and things like that. And so I will guess that the size of my favorite isogeny class is the number of elliptic curves over FQ times the probability that the trace of Frobenius of some elliptic curve is this number A. And then I will misinterpret the Sadotape conjectures and theorems as saying that this means that the chance of getting this angle is exactly sine squared theta, and then when you get off, instead of expressing it in angle land, you express it in terms of the trace, what you get is the square root of 4q minus a squared, and we now recover the same incorrect estimate of square root of q, so it's maybe a decent baseline. By the way, I should thank at some point, and it might as well be now, Everett Howe for explaining to me why it is there's this strong compatibility between Sadotape and actually Brouwer-Siegel, the same Brouwer-Siegel theorem that showed up early on in Henry's talk for thinking about how these numbers might be distributed. But this can't be right either. And so one reason is that just because there's a distribution, sine squared theta, it doesn't mean that I can actually count the probability of my favorite event at one measure 0 point and compute it like even, as bad an analyst as I am, I know that I'm not supposed to do that. And I also anticipate that somehow there should be some arithmetic meaning in the sizes of these isogeny classes, and running around talking about things like square root of 4q minus a squared isn't going to give me a lot of arithmetic. Oh well. But now I dimly recall not just that there's this Sadotape distribution, but there are other manifestations of equidistribution, other things attached to elliptic curves which are equidistributed. So I want you to kind of mentally squint in the sense of like suppressing quantifiers. And you'll know that you've heard statements like this before, that if you take Frobenius elements of elliptic curves in some sense are equidistributed mod L. And these are I'll say a little more about this, but we've seen kind of echoes of this in Kodakara's talk before mine. And they're equidistributed, not just mod L, but mod L squared and L cubed, and you can put these things together if you're so inclined. And moreover, what happens at L1 at a prime L1 has nothing to do with what happens at a prime L2. That can't literally be true always, right? Because there's independence of L in one way, but in another way, like the representation on the 3 torsion has nothing to do with the representation on the 5 torsion, typically, when you have these adelically big elliptic curves. And so you might say, all right, I'm going to define a local density, this new sub-L of AQ. And what I'm going to do for a given L is I'm going to look at the number of 2 by 2 matrices over Z mod L to the n for which the trace and determinant are the target trace and determinant which define the characteristic polynomial of Frobenius that I care about to determine my isogeny class. Unfortunately, there aren't that many of those relative to the size of GL2. So if you ask this question for any particular thing, you'll just get 0 and the thing dies. So if instead you decide to normalize, and for now we can just say, how do you make the green light go? Oh, yeah, okay. There, right, sorry. So the effect of this, for now, we'll just leave it as this makes this number be close to 1. And this might be thought of as some way of thinking about how likely is this characteristic polynomial compared to any other characteristic polynomial, normalized in such a way to get, so that the answer isn't too far from 1. A slightly more principled way of getting at this kind of quantity is if we take GL2 of ZL, there's a map to the space of characteristic polynomials. And again, we can, using our Sadotape trick, we can take the measure on GL2 of ZL, it's compact, I'll give it measure 1, push that forward to the space of characteristic polynomials, and then what this measure does is it says how often do characteristic polynomials like this happen when you choose randomly from an element of GL2 of ZL. And so for want of a better idea, I'm just going to multiply together everything I can think of, right? So there's the square root of Q term, and maybe there's a Sadotape term at infinity, and then no one's going to literally stop me from multiplying all these factors at L together. This is garbage though, right? And there are any number of critiques you might level against this kind of analysis. For now, I will just say that if you want equidistribution in the L torsion, you better sample your elliptic curves from some finite field Q, which is much bigger than L. It's unreasonable to expect all the elliptic curves over F17 to have their Frobenius elements evenly distributed mod a million and whatever the number. Okay. So it's especially galling that Gekeler is able to prove this theorem. And what he does is the following. So this is in work in 2003. He has this really incredible formula. And so at L, he does just what I was kind of advocating on the previous slide, where forming these local terms, like how likely is this characteristic polynomial compared to any other? And he does something similar at P, except that Frobenius isn't invertible at P, so he counts 2 by 2 matrices instead of 2 by 2 invertible matrices, but he does the same thing there. He has a Sadotape term. He multiplies it all together, and he gets the right answer. Let's contemplate that for a minute. So
Gekeler's result is only for FP.
Yes, so here.
Can you comment on that? Why not for FQ?
I'll try to explain what he does, and then it will be quasi-clear why he's working with P and not Q. And then we'll remove that restriction in a bit. Sorry, Alina's question, it was a good one, is what happened to the Q? Why are we stuck with P right now? And I'll give an answer to that in a minute and a better answer in about 10. But thanks. Other questions or objections or insights? Off we go. If you read his paper, it's actually not entirely clear kind of why in some moral sense it works, but I can show you how it works, and it goes like this. So let's let delta be the discriminant of this polynomial. and let k be q join the square root of delta. So this is basically the field of endomorphisms, or the endomorphism algebra. And suppose, just to make my life easier, that the ring of integers is this order, z adjoint t mod f. Then there is a class number whose job it is to count this isogeny class, and so we just do that. And this, by the way, is where I could invoke Brouwer-Siegel incorrectly and say, oh, I'm done. So there's an analytic class number formula, and I'm hoping for your sake that you know it better than I do. But roughly what it says is that if you're so inclined, you can compute the size you can compute this class number by evaluating an L series attached to the quadratic character associated to k as an Euler product. And so what you get is, so roughly the class number is a product of a bunch of terms like this. And then, if you're stuck in the back of somebody else's talk, you can just start computing these terms by hand, like just compute with 2x2 matrices, and you'll find that this number here is this number over here for no better reason, perhaps, than the fact that you know how to compute both sides and they happen to agree. There are at least two questions which remain after this work. One of them is there a pure thought proof of Gekeler's theorem that doesn't require you to compute with a zillion matrices? Another is there an analog for isogeny classes of principally polarized abelian varieties? And since this is the animating question for me, it will maybe sort of better excuse my behavior in a number of your talks where I'm the guy in the back who says, what about principal polarizations? So here's how you can upgrade the whole situation to at least start trying to think about what happens for abelian varieties. So now suppose instead of an elliptic curve, you have a principally polarized abelian variety x over fq. The Frobenius still acts on the Tate modules and the rational version of the Tate module. And Tate's theorem, a theorem of Tate says that the unpolarized isogeny class of x is completely determined by the characteristic polynomial of the Frobenius element. There's some extra data floating around because I insist on my abelian varieties being polarized. So lambda, via, say, its first Chern class and a couple of dualities, induces a symplectic pairing on any of the rational Tate modules. And so what x lambda determines is not just the characteristic polynomial of Frobenius, but something a tiny bit more subtle, which is a conjugacy class inside a symplectic group, or inside a group of symplectic similitudes, reflecting the fact that I have not just the abelian variety, but this polarization. And so the result I want to tell you about is that the weighted cardinality, let x be a simple, ordinary, principally polarized abelian variety. Then it's, the size of its isogeny class can be written as, has this product formula like this. We're still writing this down, but as a kind of proof of concept, the g equals 1 case, you can read the elliptic curve case, you can read about in the Pacific Journal of Math. For all but finitely many L, the term at L is a relatively naive one. It says, show me the number of symplectic matrices mod L which look like mine, where look like means are conjugate to, and normalize by the average number of things in a conjugacy class. Of course, for all but finitely many L means that this thing is, I have to give an honest result for an honest definition for every L, otherwise the whole statement is vacuous, right? Because I could just hold back one L and then define it to be whatever it has to be to make the whole thing work. But we were a little more principled than that. And this Sadotape term which shows up there is basically the discriminant of f divided by the discriminant of the real Wave polynomial with some appropriate normalization. Here's why it works. So there's a beautiful theorem due to Langlands in the case of g equals 1 and Kottwitz in much greater generality, which lets us compute these isogeny classes in some entirely different way. And in the off chance that you didn't make it this far into Kottwitz's amazing 100-page paper, I want to tell you a little bit about it. So for our abelian variety, we're allowed to think about h upper p this is the prime to p h1. So this is the product of all the Tate modules at once. And it has a linear operator corresponding to Frobenius. And at P, there's the crystalline cohomology, and it has a semilinear operator, semilinear operators Frobenius and Verschiebung. We'll need to let Y upper P be the set of lattices in these Tate modules, and Y lower P is the set of lattices which are stable under F and V in the crystalline cohomology. And we need to talk about the automorphism group of this polarized abelian variety. And the right thing to do is to think about the thing which hands you back endomorphisms of this abelian variety up to isogeny, which preserve the polarization up to a multiple. Please do so. OK, great. So, and then there's a very, I'm sorry. That's the Witt vector is over FQ, and then its fraction field will be inevitably QQ. Sorry. Other remarks, questions, be they notational or beyond? OK. And so one thing I want to get across somehow is that, like, one shouldn't go lightly into the work of Langlands and Kottwitz, perhaps. So, like, and Kottwitz's work in particular is kind of magisterial. He's trying to compute express the number of points on a Shimura variety in terms of trace type stuff. But what I'm using here is a tiny tool that he uses, and this is understandable by mortals. This is something you can explain in a bar. So, like, I feel like we're using fair means somehow, even though the inspiration is comes from the work that I'm adapting here was done in the service of very deep mathematics, but it itself is not hard. And so there's a bijection between the isogeny class that we care about and pairs consisting of lattices modulo the action of our endomorphism group. And this takes a little while to convince yourself of, but the idea is really simple. If you have an isogeny between abelian varieties, then you get a map from like any linear algebra data associated to one to any linear algebra data associated to the other. You just have to be conscientious about keeping track of this. Then we can turn all of this into a set of statements about lattices and group elements. So G is the group of symplectic similitudes. And this is the same GSP that was in the talk before by Kojikaru. And so if we choose some isomorphisms, then automorphisms of these, all these Tate models in this crystalline cohomology are the same as symplectic similitudes of any space that you like. So inside this package of things, so gamma naught is going to be, how does Frobenius act at the prime to p Tate modules? And delta naught is, how does the semilinear Frobenius act on the crystalline cohomology? And we'll define the centralizer of gamma naught. Sorry, the subscript means centralizer here. And then for here, the right thing to do isn't the centralizer exactly, but the twisted centralizer. So they commute up to an action of sigma. And the reason is because we have this sigma linearity. It's not a linear operator, it's a sigma linear operator. So when the dust settles, this is the right. When you change coordinates, this sort of twisted conjugation tells you how your operator acts in the new basis. And there are some compatibilities between this perhaps exotic-looking group theoretic data and things that we actually know what they are, like characteristic polynomials. And there's also a relationship between the kind of the P Frobenius and the Q Frobenius. And that what Langlands proves for G equals 1 and what Kottwitz proves in kind of horrific generality is that if you want to, you can compute the size of an isogeny class. Sorry, I've now dropped Q from the notation because it's been built into everything else. As there's some global term, and there is an orbital integral like this, where this is the integral over the finite prime to p adels, and then there's something even more complicated happening at the p at p. But the idea is actually pretty simple. Remember, we're supposed to be counting lattices, say, prime to p lattices. And to get from I can always get from one lattice to another by an element of GSP. And so then what I'm saying is I want to count not just all other lattices, but ones which are stable under Frobenius, where my Frobenius acts as an automorphism and not just an endomorphism. And somehow, if instead of indexing things by the lattice, but by the way Frobenius acts on this other lattice, you wind up doing this, and then asking for the characteristic function of ZL, or the Tate module says, make sure this Frobenius-like thing stabilizes the Tate, is an automorphism of the Tate module. And then you do something similar, but worse at P. And so then at this point, it becomes a kind of reverse engineering game. So I want to write down things which look kind of natural, local factors, whose job it is secretly to compute integrals like this. And there are a couple of linear algebraic wrinkles which come up, which are probably very familiar to you, but I got bit by them a couple of times before I learned how to walk around them. So the obvious one is that conjugacy is a little subtle in any group but GLN, in the sense that conjugacy and semi-simple elements in GLN have the same characteristic polynomial if and only if they're conjugate, and that fails for basically every other group. So we have to be cognizant of that. The other thing that happens is that just because you have two integral matrices, which are conjugate, say, with Q coefficients, it doesn't follow that they're conjugate with Z coefficients. So you have to be a little crafty about that as well. And I just realized I'm going to arbitrarily award myself 2 more minutes. Does that sound, or sorry, but, okay. All right. So it turns out that to make the right definition, we need to work with kind of integral-looking symplectic matrices. So they are invertible with QL coefficients, but perhaps not with ZL coefficients, even though their coefficients lie there. And then as a proxy for conjugating by elements which are no longer invertible mod L, I'll say that maybe I can let them sort of have lots of matrices which commute, which, so multiplying on the left by one is like multiplying on the right by the other. Sorry, one thing I should have singled out in here is M sub D will be the things of bounded determinant D. So their determinant is at worst divisible by L to the D. The reason to go through that last slide at all, if you believe there's a reason for the whole talk at all, I guess, is that the definition we need to make is, so for gamma naught is the thing which measures our isogeny class somehow. And then we have to define this conjugacy class-like thing, mod L to the n, where you're allowed to kind of quasi-conjugate by matrices of bounded determinant. And then we'll define this local factor as how big is this quasi-conjugacy class relative to any other quasi-conjugacy class. That's a terrible name. I'll think of a better one soon, I promise. This looks horrible, but at least for all but finitely many primes, it's knowable, right? So for all but finitely many primes, this says how many elements of GSP of Z mod L have this characteristic polynomial as opposed to some other. And then it's clear what we have to do, right? So the Kottwitz formula says, I will give you the size of this isogeny class, but you have to integrate against a certain measure, which gives the integral points measure 1. Whereas it turns out these things I was defining on the last slide, you can say, oh, these are obviously, for certain values of obvious, also equal to an integral over G of ZL. It's just with a different measure. And so then the theorem just reduces to a relation of one kind of measure on G of ZL to another. And then you have to do some non-trivial horsing around, by which I mean invoke the fundamental lemma to move questions from sigma conjugacy in QQ to honest conjugacy in ZP. But if you do that, you'll get the theorem too. Thanks.